equation, where we had the Fock operator. Okay, so in the last lecture, we had arrived at the canonical Hartree-Fock equation, which has the Fock operator and then the spin orbitals, which are obtained by variational minimization of the energy. And we found that the equation that we need to solve is basically this, which is an looks like an eigenvalue equation, but it still has an operator. It's not a matrix eigenvalue equation yet. And there, every spin orbital that we obtain, the optimized one, is associated with an energy which we called the orbital energy, the spin orbital energy. And I runs over all the functions that you use to express the spin orbitals. We will talk about that a little later. Okay. And we will get as many spin orbitals as the functions that we start with. But just hold on, you will not understand this at the moment. But we will talk about it. Okay, this is this. Now, if we also saw that the orbital energies are basically the diagonal matrix elements of the Fock operator. Why is that? If we project with chi j, then because of the orthonormality of the spin orbitals, this is a delta ij. So the Fock matrix, as it is called, is a diagonal matrix in the basis of the spin orbitals. So when you have the optimized spin orbitals, then the matrix element of the Fock, then matrix of the Fock operator is diagonal. Okay. But what sort of energies are these? So let's see. So then I write epsilon I is chi I, F chi I. And in recalling that F has two parts, there is a one electron part, that is the nuclear electron attraction and the kinetic energy of the electron in spin orbital chi I. That is there. Then there is the Coulomb part, so that is chi I some B JB, that is the Coulomb operator. Chi I minus the exchange part. And the matrix element of the individual Coulomb operators, those were the Coulomb integrals. So I can further simplify this to some B, IB, IB minus some B, IB, BI. Okay. And let me write this also in. So when I'm writing IB, I just mean chi. I'm just not writing the chi's anymore. This is IHI. I'm also writing it in Mulligan, just to be clear. Fine. So now let us look at some particular orbital. So this is the expression for the energy of the ith orbital. So what does it mean? So you see that if there is an electron in I, so then I'm calling the occupied. So the occupied ones are called A, B, C, D in Zavoostland, and the empty ones are called PQ, RS or something. Okay. So I will say A, where A is a occupied orbital. Then this is equal to AHA, that is the one electron part of the energy, and sum over all the other occupied. So B, that is why the sum is always over B. So the repulsions only occur with when the spin orbitals are occupied. Okay. So B runs only over the occupied orbitals, or B is equal to 1 to n, where capital N is the number of electrons, which is equal to number of occupied spin orbitals. And I is so far a general index for any spin orbital. So when I is an occupied orbital, then when you take the Coulomb in exchange, then when B is equal to A, there is zero contribution. So the sum basically runs over B not equal to A. Sorry for mixing up notations. That is not good. Okay. But if I consider some orbital which is not occupied, those are called the virtual orbitals. That is a name. I will tell you why we get the virtual orbitals in just a moment. Then you have the one electron part, that is fine. But in the two electron part, my sum runs over all the occupied ones. So this is still the full sum. Okay. So then we see there is a fundamental difference between the physical meaning of the energy of occupied orbitals and the energy of the unoccupied orbitals. So for the occupied ones, the orbital energy represents the energy of the electron itself and its repulsion with n minus 1 electrons. So this runs up to n minus 1. So with the other electrons. Okay. But the energy of an unoccupied or virtual orbital, this is the energy of the electron itself. So if you have an electron, if you put an electron in R, then it will have the energy, which is the kinetic energy of the electron itself, plus the attraction it gets from the nucleus, and its repulsion with all n other electrons. So this is the energy of an extra electron if you put it in. So if you have an n electron system and you do the Hartree-Fock for it, so you have done the Hartree-Fock method or solve the Hartree-Fock equation for the n electron system, then energies of the orbitals that you obtain when they are occupied I'm just doing a rough thing. It is not necessarily like this. I mean, you could have these two of the same energy as well, or they could be different. Then epsilon A is the actual energy of an electron in this system. But epsilon R is the energy that an electron would get if you put it in. So if you put in another electron, then the energy that it would get is epsilon R. So is the difference clear? So if you move an electron from an occupied orbital to epsilon R, then it would have physically got experienced repulsions from n minus 1 electrons. But the orbital energy of that orbital is not that energy, because the orbital energy of the empty orbital contains repulsions from all n electrons. So then what is it? Then epsilon A is the, okay, so epsilon A is the actual energy of an electron in spin orbital chi A. Epsilon R is the energy that an additional electron would get if it was placed in chi R. Fine. Then epsilon R, so what do you usually call the energy that an additional electron gets if it is placed in a molecule? So that is what is called the electron affinity of the system, right? So then the energy of the empty orbitals are the electron affinities. And when you supply energy to a molecule and you remove an electron, then the amount of energy required is called the ionization potential, and that is epsilon A for the occupied orbitals. So is that clear? So when you solve the Hartree-Fock equation, you get a set of spin orbitals in some order of energy. You arrange them from lowest energy to highest energy, like we were talking about in the last class, and you fill the lowest n spin orbitals to get the ground state of the system. Okay. Now, each spin orbital is associated with some energy, both the occupied ones as well as the unoccupied ones. Now, for the occupied ones, the orbital energy is the energy that you would need to liberate the electron. That is similar to what you know before. That this is the ionization potential, and this electron has a binding energy of epsilon A. So the occupied orbitals normally have a negative energy, which means that they are bound to the nucleus, the electrons in the occupied orbitals. And when we supply the epsilon A amount of energy, then an electron from orbital chi A will get released. So this is the ionization potential. And for epsilon R, when you put in an electron, that is into that. So if there is if epsilon R is positive, then energy will be needed to put that electron in, and if epsilon R is negative, then energy will be released when you put that electron in. So this is what the energies mean. So why is it necessary to understand this very clearly? Because if you remove an electron from epsilon A and put it in epsilon R, then simply subtracting epsilon A and adding epsilon R will not give you the correct energy of the system, even in the Hartree-Fock picture. Because putting an electron in epsilon R means you're adding some extra repulsions. You're adding some extra repulsions because epsilon R does not see that epsilon A has become vacant. Is that clear? Just think about it. I think it is not. It is important to remember this actually, especially when you do correlation theories, and also when you do calculations with Hartree-Fock. So the energy of the virtual orbitals are not are the electron affinities and uh, not the energies of orbitals to which you excite. So this is important to remember. And then okay, so this is the Koopman's, and this fact is called the Koopman's theorem. So there is a statement. So let me open the Gaussian and I will read out the exact statement for you. It takes longer to scroll through a PDF and turn pages. Okay. So the exact theorem is that given an n electron Hartree-Fock single determinant psi 0 n with occupied and virtual spin orbital energies epsilon a and r, then the ionization potential to produce an n minus 1 electron single determinant with identical spin orbitals obtained by removing an electron from spin orbital chi a and the electron affinity to produce an n plus 1 electron single determinant n plus 1 psi r with identical spin orbitals obtained by adding an electron to spin orbital chi r are just minus epsilon a and minus epsilon r respectively. Okay, so this theorem contains everything that we spoke about right now except for an additional clause that it says with identical spin orbitals. Can anyone tell me why it is important to mention this?
What is the page number?
In my book, it is 127. So why do you think it is necessary to put in this clause that the n plus 1 system and the n minus 1 system need to have identical spin orbitals for me to identify the orbital energies of the n orbital system with the IP and the EA? So if I calculated the energy of the n electron system, then I calculate the energy of the n minus 1 electron system and I subtract it. Would I get the orbital energy of the orbital that I have ionized? That's at the Hartree-Fock level. Do you get my question? that I do two Hartree-Fock calculations, one for the n electron system, one for the n minus 1 electron system, and I subtract the two energies. So that tells me the ionization energy, right? So would it be the same as the orbital energy of the orbital that I have removed an electron from? No, actually it would not, because the optimized orbital for the n minus 1 or n plus 1 systems, they would in general be different from the orbitals that you get when you optimize them for the n electron system. So the fact that we are calling epsilon A and epsilon R IP and EA, that is with the clause that I am constructing now the n minus 1 Slater determinant from the orbitals of the n electron system. So then how is this important, or how different are these energies? So the thing is that there is, so when you do it depends on the experiment that you do. So if it's a very fast experiment, then often the effect is that the electron is removed without the rest of the electrons adjusting themselves. So if it's a very fast ionization process, then the energy that you need is actually what is called the unrelaxed ionization potential, orbital energy. However, if you do something like a slow ionization, say thermal ionization or something, then the electrons have a lot of time to adjust, and then the energy that would be closer is if you do two separate Hartree-Fock calculations and take the difference. Is the difference clear to you? So both types of ionization potentials have some importance depending on what sort of experiments you are comparing. Fine. Is this clear? Okay. I hope it is clear. Anyway. So that is that. So this is the significance of the Koopman's theorem. And we need to keep remembering this, especially when we do correlation methods and perturbation methods. So there, I can give you like a preview. The thing is that you take the virtual orbitals or the unoccupied orbitals that you obtain from Hartree-Fock as if to represent, you construct excited determinants from these, like we were doing before, that you remove chi A, remove an electron from chi A and put an electron in chi R, and then you assume that the energy of that system is simply the energy of this new determinant. But that is not strictly true. So the energies of the virtual orbitals that you get from a Hartree-Fock calculation are in a way less accurate than the energies of the occupied orbital. So these statements always depend on the context. So if you're talking about calculating an electron affinity, then the virtual and an IP, then the orbital energies are all on equal footing. So you're removing an electron and putting an electron. But when you're talking about excitation, then the orbital from which you remove the energy, that energy is more correct than the orbital into which you are putting the electron. So you have to think, yeah. So that is like a, so that this becomes important when we do the correlation methods. So you have to keep that in mind. Okay. Then there is the Brillouin theorem, but I will come back to it later after we finish the Hartree-Fock, when it's clearer to you what the excited determinants and mixing of excited determinants means. We will now go back to trying to solve the equation. So now we spoke about what the energies of the orbitals mean. But now let's see how will we obtain these energies, also how we will obtain the spin orbitals. So next is solving. F chi I equal to epsilon I chi I. So in the first place, what we have to do is we have to write the spin orbitals in terms of some sort of known functions. Now the thing is, so chi I has a spatial part and chi I has a spin part. So chi I x1 is equal to psi I r1 into either alpha omega 1 or beta omega 1, depending on what type of spin orbital this is. And these spin functions are entirely theoretical constructs. So we don't have actual functional representations or mathematical representations of alpha and beta, and neither do we know what the spin coordinates mean. So this is something that has to be analytically taken out before you can do any numerical calculation. So the first thing you have to do is now write this equation only in terms of spatial orbitals. So for that, the first thing we will do is we will take the closed shell system, which means that number of alpha electrons is equal to number of beta electrons in the system, and they are all paired up. And the description that I will take is a restricted description, which means that if chi I x1 is equal to psi I r1 alpha omega 1, then chi I bar x1, which is the corresponding beta, also has the same spatial part. Only the spin part is different. So it's this and this are same. When they are not same, say if I wrote psi and psi prime, then it would be called an unrestricted description. But for now, we will talk about the restricted description. Okay? And then we will go back to this Fock operator equation and remove the spin coordinates. So how will we do that? So we will simply do this. So we're doing it only for the alpha case. The beta case will be exactly the same. So we will do d omega 1 alpha star omega 1. And we will apply this on the equation. So what do we get? So we get integration d omega 1 alpha star omega 1 f operator, which depends on x1. And then you have the spin part of the chi I, which is alpha omega 1. And then you have the remaining spatial part of chi I, which is psi I r1. This is the left hand side. Then on the right hand side, you have epsilon I. And that is, of course, easy. So d omega 1 alpha star omega 1 alpha omega 1 into psi I r1. This is called the Fock operator in the spatial orbital basis. So you define this as the Fock operator R1. And you have psi I R1, epsilon I. The spin part is normalized, so that's 1, and you have psi I R1. Okay. So this is now, so this is exactly looks like my spin orbital Fock operator equation and or canonical Hartree-Fock equation. This is the then canonical Hartree-Fock equation in spatial orbital basis. Now the spatial orbitals we can represent using known functions. Okay? And this is what we will do. So let's see. So what remains, of course, is to see what the energies of the spatial orbitals turn out to be. If they are different or same as the spin orbitals, that is something we must check now, of course. So to do that, what we have to do is find out the matrix elements of the spatial Fock operator. Let's do that. So this is my equation, and then I can open out the Fock operator as H R1. That is fine, right? And you have the sum B JB minus KB. This is in the spin orbital basis. But now we don't know what it looks like. So we want to know what this would look like. So we write this now explicitly. That's the problem. So we have written this from the definition. So d omega 1, integration d omega 1 alpha star omega 1 is a part of this definition. And then we have written the Fock operator in so fx1 as r1 to the Coulomb part of it as r1 to inverse, and then the integral involves chi c. So this is actually from the form of JB. This is from JB in the spin orbital representation. And you have this integral. Then you have the other one, which is okay. I have minus C. Okay. So this is now the sums have been opened out. So the sum over the spin orbitals has been split into the alpha and beta up to n by 2. Okay. So does that make sense to you or not? So the spin orbital Fock operator, that has been opened up into two sums. So the first two come from the Coulomb part and the next two come from the exchange part. And every spin orbital involved in the Fock operator, that has been written as a product of spatial and spin. And the integration is performed over both omega 1, omega 2. So there was one integration already in the definition of the operator, which was d omega 2 r2. And because of the conversion of the Fock operator from spin orbital to spatial, we have an additional integration d omega 1. And on the left hand side, then we have a Fock operator which depends on r. So the other three coordinates, omega 1, omega 2, and r2, they have been integrated. So when we do the integrations here, so the ones which we can do are omega 1 and omega 2 basically. So then let's do the first one. So omega 1 comes from alpha omega 1, alpha star omega 1, alpha omega 1. So that is 1, no problem. For omega 2, you have alpha star omega 2, alpha omega 2, also 1, no problem. Let me just write this. This nothing was needed here. you have 1 into 1, and you have the remaining, which is dr2 psi c r2 star r1 to inverse psi c r2 acting on psi j r1. So this would now become my operator. Similarly, let's look at the second one. So for omega 1, you have alpha star omega 1, alpha omega 1, that is 1. Then for omega 2, the terms which depend on it are beta star omega 2, beta omega 2, so that is also 1. So no problem. So you have 1, 1, and what is left is integration dr2 psi c star r2 r1 to inverse psi c r2 psi j r1. Now this is my new Coulomb operator. Then in the exchange parts, what do we have? We have sum c equal to 1 to n by 2. Omega 1 is alpha star omega 1, alpha omega 1, so that is 1. Then for omega 2, you have alpha star omega 2, alpha omega 2, that is also 1. So the rest is remains dr2 psi c star r2 r1 to inverse psi c r1 psi c r1, yes, and acting on psi j r2. Then this would be the exchange operator. Then let's look at the next last term. So omega 1 is alpha star omega 1, beta omega 1. So that itself, that is 0. So you have 0. So we lost one term. And notice that the first two terms, they are also the same. So you will get two of these. So you have HR1 psi J1, that is unchanged, plus 2 times sum C equal to 1 by n by 2. And this I can write now as a spatial Coulomb operator. Let's say I call that JC, acting on psi JR1. JC R1, and you have now a single exchange term, so that's C equal to 1 to n by 2. We can now again introduce the permutation operator, if you remember it from last class. So then we can say that this is integration dr2 psi c star r2 r1 to inverse p12 psi c r1 psi jr of psi c r2 psi jr1 r1, and we call this now KC R1. So I have HR1 plus sum C equal to 1 to n by 2 JC minus KC R1 R1, and this acting on psi J R1. So now we have obtained the operator form for the spatial Fock operator as well. So for the spatial Fock operator, we can then say that FR1 is equal to HR1 plus sum C equal to 1 to n by 2, which is the number of spatial orbitals, 2JC R1 minus KC R1. There. So what is the difference? So in the spin orbital case, we didn't have this factor 2. So that is the only difference between the definition of the spin orbital Fock operator and the spatial orbital Fock operator. So we only have 4 minutes left, so I will not start on the next part. So we were unable to do the Rothan equations today. We'll do it tomorrow then. And do you have any questions about today or any other thing? Anyone?
Hello,
Yeah, yeah.
madam. Hello,
Yes, yes. Go ahead.
no, the rules for uh, Koopman and the another one. Uh,
Yeah, you can ask me. Hello, I can't hear you. You're saying something.
Koopman theorem and Rothan equation. Not clear. I just
Oh, the Rothan equation we haven't. I didn't manage to teach you today. We only we only did Koopman's theorem, and then so the Rothan equations you need to go over to the spatial equation. So I just started on that. So the actual Rothan equation is the matrix equation which you need to solve. We haven't got there yet.
uh, and too many calculations.
Yeah, but this you only need to do once. After that, you will only be sitting on the computer and running things. So what is important here is just the difference between the various things. Like in the spin orbital, you don't have to. In spatial, you have to. Okay. Then why it is necessary to go to the spatial orbital. Then or how to do it. Like why do we why does this affect the Fock operator, like going from spin orbital to spatial orbital? That is because the Fock operator contains the orbitals. The Hamiltonian is independent of spin orbital or spatial orbital or anything. It only depends on the actual so you can say the Hamiltonian is only purely spatial, at least the Hamiltonian we are dealing with now. So that is there. You just need to know like how what came. The actual derivations you might need it for the exams now, but afterwards you will not need it. Don't worry. Actually, they are not very difficult. You see, they're just multiplication and stuff. You just have to write a lot and be careful. I think that is the problem with the quantum chemistry. You have to write a lot, even though the calculations are simple. Okay. So someone
Ma'am,
please stop the recording. Yeah, okay. Yeah, go ahead.
what is the syllabus for Saturday's test?